Hi folks, and welcome to this video. It's quite a long one because we're going to talk about various different aspects of circuits. So do feel free to pause, take notes, to replay any parts that have gone a bit quick, and as ever, make sure you ask questions when things are not clear. So let's get started. The first circuit that we're going to look at is the one that you can see on the screen, which is an example of a series circuit. Now we know that this is a series circuit because there's simply one loop. You've got a 5-volt cell or battery connected to a 20 ohm and a 10 ohm light bulb. So the way we would describe this is we'd say that the cell is connected in series with the two lamps. Now, we're just going to go over a few basic rules. We're not going to talk about where these necessarily come from, but they're things that we observe when we use these series circuits. The first one is that if we measure the current anywhere in this circuit, then we'd notice that the current is the same at any point. Now, sometimes we write this way: I is equal to I1, I2. Just to explain these symbols, I is the current drawn from the battery. I1 would be the current through one of those lamps. So let's say the first one is I1 and the second one I2. So basically we're saying here that the current measured anywhere in the circuit is the same. Okay. Now, the next point that we make is that when we measure the potential difference, we notice that the potential differences always add up to what's called the electromotive force. That's the EMF of the power supply. Now, the EMF of this power supply is 5, and we're going to represent that with a capital V. Now, if we were to measure the potential difference across the 10 ohm light bulb, for example, and then measure the potential difference across the 20 ohm light bulb, they might be different. They should be different. However, they would always add up to equal 5. So the sum of those two potential differences, V1 and V2, is equal to the potential difference, or the EMF, from our battery. Okay, essentially this is energy conservation. Everything going in equals everything coming out again. So 5 volts come in, 5 volts come out. Now, the main reason we're looking at these circuits is actually not to think about potentials and currents. We're looking at resistance. Now, when we have two resistances connected in series, what happens there is the resistance increases. Now, the reason for this is because our electrons, or our charge in general, is having to pass through more material and therefore experiencing a greater resistance to its motion. Now, the nice thing about this is that actually the rule for series is very simple. When we want to get the total resistance, or effective resistance, R, all we do is add up the resistances that we know. So in this case, we've got a 10 and a 20. Well, the 10 and the 20 add up together to make a nice 30 ohms. Now, this is similar to when we make, for example, a longer resistor. You'll have learned in your studies of resistivity that when the resistance wire becomes longer, the resistance increases. And that's effectively what we're doing here. By adding our resistances in series, we're getting more resistance because they're basically making that resistance longer. Okay, now what we could do here is calculate the current. You'll notice that the current has been blacked out there so that we can't see it. Well, let's have a look at what the value here is. In this case, the current is 0.17 amps. Now, where does that come from? Well, in this case, we know that the resistance is 30. We know that the potential difference across these two bulbs must add up to make 5. And so therefore, we can use our equation, which is I equal to V over R. Well, V is 5, R is 30, and then we've got 0.17. So, okay, if it comes up on your calculator with 0.167, it's about the same. Okay, so this is just the information about our series circuits. At this stage, I would suggest you pause, just sort of check that you know what's going on here before we move on to talk about parallel, which is a little bit more complicated. All right, I'm assuming that we've digested series circuits. Let's talk about parallel. Now, here we've got the same set of components. We've got a cell, a lamp, and another lamp with 10 ohms and 20 ohms respectively. However, this time we've arranged them in a different way. This is a parallel circuit. And what you notice here is there's multiple loops. Okay, so we've got multiple loops in our circuit, and this is where the rules become a bit different. Okay, let's take the example of currents. Well, Sorry, let's take potential difference first, sorry. When we measure the potential difference across each of these guys, we notice now that they have the same potential difference. Okay, so the potential difference V is going to be equal to V1 is equal to V2. And if we're looking at this circuit, you'll notice there we've got an EMF of 5 volts in my battery. And that means that if I were to measure the potential difference across either of those lamps, I'd get 5 volts. 5 comes in, 5 comes out. So they each have the same potential difference. Now let's get on to current. Current leaves the battery, and then when it reaches one of these junction points where the loops meet each other, it has a choice of going either through the 10 ohm or the 20 ohm resistor. Now, due to charge conservation, it follows that the current drawn from the supply, that's big I, is equal to the current going through I1 plus I2. What that really means is that the charge has a choice of paths to go through, and it will go out through either the 10 or the 20 ohm, come back around the other side, and then meet at the other point and back round through the battery again. You'll notice there, this is the opposite to our series circuit, where we said the current was the same in every place. Now, the result of this, and again, you don't need to necessarily know where this comes from, is that excuse me, when we connect our components in parallel, this will decrease our resistance. It means that we have a slightly different equation for calculating the effective or total resistance of resistors connected in parallel. I'll just show you the equation now. Here we've got 1 over R is equal to 1 over R1 plus 1 over R2. Remember, for series, this was R equal R1 plus R2. So it's a different kind of equation. Now, what we could just do here is we'll just have a little look at what this means for our circuit. Okay, we've got 2 resistors here. We've got 1 over 10 and 1 over 20. Okay, what that means, we're going to have to do a little bit of maths to make sure that we can get that 1 over R is equal to 1 over 20 plus 1 over 10. That's 1 over 20 plus 2 over 20, okay, which is equal to 3 over 20. So we know that 1 over R, 1 over the effective resistance, is 3 over 20. Now, a common step that a lot of people forget is to then remember we want to calculate R, we want to calculate the total or effective resistance. Well, we need to flip at 20 over 3 because we've got the reciprocal of the resistance, not the actual value. And so that ends up with a 6.67. Notice there, our resistance has gone down. Okay, we started off with a 10 ohm and a 20 ohm resistor. We've added them together in parallel, and we've resulted in a lower resistance than either of those components that are in there. Okay, so key point being here is that we've reduced the resistance. We're taking the 2 resistors, identical to the ones before in the series circuit, arranged them a different way, and somehow reduced the effective resistance of those 2 resistors. Now, what does this mean about the current? Well, we've got a lower resistance, so we're expecting a larger value of current. And if I just have a little look there about what our current value is, we can see 0.75, and that's consistent with our understanding of resistance. The lower resistance brings a higher current. Now, where does that 0.75 come from? Again, we're going to use I equal V over R. This time, we know V is 5 volts again. This time, our R is 6.67. And if you put those numbers into your calculator, you're going to get a 0.75 amps. What this means is that we're going to draw a larger current from our battery. Okay, so I think that's a good point to stop. What we've done there is we've looked at the different arrangements of resistors in series and in parallel, and we've looked at how their resistances add together in both cases. We've done some example calculations, and we're remembering that point, really key one, that when we're working in parallel, we have a trickier operation to perform, namely that we need to remember to flip the numbers at the end rather than delivering simply the 1 over R value. We need to calculate the total resistance as per the question that you're doing. Now, it is worth my while right at the end here saying this works for 2 resistors, it works for 3, works for 4, works for 5 resistors connected in parallel as well. And so when you're doing your problems, be sure to count the number of resistors, consider the resistors that you are working with, and make sure that you're simply adding together the terms in sequence before you come to your final answer. All right, that's enough from me. If you're in my classes, you should be getting on with some practice questions, and we'll see if we can build up to more complicated circuits. Thanks for watching.